Okay, I hope everybody can hear me, um,
Yep.
and I hope everybody can see my slides. I need to start by apologizing for not being there today. I'm very sorry. I really wanted to come, but events transpired against me somewhat this week. And thank you, Roma, for stepping in for the session chairing duties. I probably owe you a beer. I probably owe you many beers. So yes, I'm going to talk about some lead isotope work, more lead isotope work following on from Renault's talk. This time it's looking at a ferroan anorthosite and what that might tell us about kind of the early evolution of the moon and the lunar crust. So this is a bit of work that's been collaboration between myself, various people at University of Manchester, and then also at the Nordsims laboratory in the Swedish Museum of Natural History. So a little bit about the kind of general rationale for this study. So um, we want to look at the kind of evolution of the lunar crust. And so thinking in terms of the most simplistic magma ocean models, we have this idea where you have a fairly homogeneous and orthositic crust forming by flotation of plagioclase towards the end of the magma ocean crystallization. And then at the very end, you have these dregs of magma ocean melt forming this creep source, this potassium rare earth element and phosphorus enriched layer below the crust. And since this model was first proposed, there's been modifications to try and explain some of the things that we see on the moon. So, for example, the fact that you have a thicker far side crust, or the fact that we maybe have variable distribution in the creep uh, composition across the moon. And so maybe you could explain that with convection within the crystallizing magma ocean. Equally, there have been suggestions that maybe you have dipirs of varying composition, plagioclase-rich dipirs, which rise to the surface and form varying different types of an orthositic crustal material. And then as a kind of end member, we also have to consider the effect of impacts. And so Renault, I think, is kind of alluding to this when he talks about his extra source maybe generated by something that's not the LMO, I would guess, if I'm reading between the lines correctly. But yeah, potentially you could have mini magma oceans if you have very big basins forming large melt sheets, but even just the modification of the pre-existing crust. And that's a bit more what I'm going to talk about with this sample. So Renault's done a nice job of introducing a lot of the lead isotope stuff, so I can whiz through this stuff fairly quickly. I'm going to ignore the thorium to lead decay chain. I'm just going to focus on the two uranium to lead decay chains. Also bear in mind we have this 204 lead, which is the only non-daughter isotope in the system. And similarly to Renault's talk, I'm going to spend a lot of time mentioning mu values. So this is the uranium to lead ratio. And so for reference, what we see in like terrestrial mantle doesn't often get much beyond about 10, a mu value of 10. So what does that all mean? So when we're making these models, we start from a kind of primitive source composition. So we often tend to use Canyon Diablo troilite. So this is the most primitive lead isotope composition that we've measured in any meteorite. And then as geologic time goes on, the lead isotope compositions will evolve depending on the mu value along growth curves like this. And so you can think of the mu value as kind of giving oomph to the growth curve and basically shifting the composition across further if you have more uranium in the system. And so then for any given time, we can try and work out what the initial lead composition in a particular source would be at a given time. So for example, if we have a source that has a mu value of 500 and it evolves along until about 3.9 billion years, and then at that point we extract a rock from that source, then the green dot up here is what the initial lead composition of that rock would be. And then all of the other minerals within the rock would have varying different uranium to lead ratios, and they would have their own kind of growth curves over time. And if the rock is well behaved and hasn't been messed up by too many processes, everything would form a line, which is your isochron. And I'm going to say right away now, I don't have nice, pretty isochrons for my sample like Renault did. That's the nature of looking at the kind of anorthositic crust. So, yeah. So as Renaud said, we've got a lot of data for different basalts. So here's just the data that we have for Apollo basalts. And we have this model which we first suggested back in 2016, where you have two stages of lead isotope evolution on the moon. And as you can see from Renaud's talk, that's been taken even a step further and explaining some of these basaltic compositions through mixing. And that's all kind of fits quite nicely. But what's interesting is that I think both the lead isotopes and also other isotopic systems seem to agree on the fact that we have some kind of big differentiation event, potentially the end of magma ocean crystallization, somewhere around 4.4 billion years, a bit younger, perhaps. But what I should say before I move on is that this is great, but it doesn't tell us much about the crust, the formation of the lunar crust, because we think that presumably there would have been some other event at some point, which would have been the separation of the ferroan and anorthosite source coming somewhere off this grey curve for the bulk silicate moon. So that's where 15415 comes in. So this was instantly recognized by the Apollo 15 astronauts as being special. It was collected on the rim of Spur crater, and they could see straight away it had tons of plagioclase, and they were well trained to look for this, and they knew that it was very important as a potential sample of the ancient lunar crust, and it was dubbed the Genesis rock. There were some argon-argon dating studies early on, which, while they don't provide a very tight limit on the actual crystallization, they maybe provide a lower limit for crystallization age at about 4.1 billion years. That's already a red flag potentially, because that's very young for what we now think the anorthositic crust should be. So here's what we get with our lead isotope data. And I warned you I don't have nice isochrons. So what does this mean to people who aren't used to looking at lead isotope plots? Well, there's some old data for the same sample. This is from whole rock and plagioclase separates. And you can see that everything ends up on the top left-hand side here. And I will focus a bit more on that. But just to begin with, on the bottom right-hand side of this trend, I should draw your attention to the fact that where this blue cross is, that is modern terrestrial lead. And so what we have here is a mixing trend. So I really need to emphasize this is not an isochron, and we cannot get an age directly from this. But we can do some useful things with this cluster of points up at the top left-hand side, I think, because this represents some kind of initial lead composition that's then been mixed with terrestrial contamination. So where does it sit in all the data points that we have for our basalts? It sits somewhere up here, which is odd because it would suggest that you have a mu value somewhere in the region for the source of about 1,000, a uranium to lead ratio of about 1,000. And given that we're talking about very plagioclase-rich samples, which is a mineral where you have lots of lead and much less uranium, uranium's very incompatible, that mu value is far too high. Based on what we know about plagioclase trace element partitioning, you should be looking more at a mu value of, well, certainly less than 100, potentially even as low as something like 10. So let's simplify this plot. We'll take out the basalts because Renaud's done a great job of talking about the basalts. We'll just look at creep for now. And so we have our sort of, you can think of the gray line as your magma ocean evolving, and then you have your creep source evolving at the very end, or forming at the very end of magma ocean crystallization and continuing until we get this Apollo 15 creep basalt. Now, if we take what we know about uranium lead partitioning in plagioclase, we can start estimating what fan growth curves might look like. And so if we estimate that maybe a growth curve, the fan source might have formed very early, say like just after the moon formed, 4.49 billion years ago, then you'd have a growth curve that looks something like this. And then because these growth curves, both for the fan source and the creep source, I've drawn these essentially to, or calculated them, I should say, to the same end point in terms of time. And so we can create mixing lines between common time points that would correlate to what we see in 15415. And so the two mixing lines here, they correlate to ages that are about 4.1 to 4.2 billion years. And you're looking at maybe just about an addition of something like 1 to 1.5% of creep component. And because creep is that much more enriched in the incompatible trace elements, you only need that small amount to drag the composition away from the fan source here up towards the creep curve. So that's a very old fan source, but people like Lars Borg like to have suggested that potentially LMO crystallization happened very quickly, and so you could have a very young fan source. And so this, in this case, just at the very end of the magma ocean. And you get a similar age rate, slightly younger age range, but also similar kind of 1 to 1.5% of creepy lead needed to generate what we see in 15415. And it's worth pointing out that these age ranges for this mixing are very consistent with what we see in the argon-argon studies, even when you update all the argon-argon ages for modern decay.
2 minutes.
Thank you. Decay rates. So how did this mixing happen? I think there's two likely candidates. One is that you have some sort of mixing in the sources as the formation of the rock was occurring, in which case the mixing time would roughly equate to the crystallization time, probably. But we should also then expect that we might see the mixing in other elements, particularly in some more refractory elements. The other alternative, I think, is that the mixing is due to some kind of mobilization of lead during an impact event, in which case the mixing time is younger than the crystallization age, but it may only be evident in more volatile components. So let's have a look at what evidence we have and see if we can pick between these two options. So there's generally low trace elements in the sample, and there's also other isotope systematics to show little sign of kind of more refractory creep components in the sample. So there's very little uranium and lead compared to uranium and thorium compared to lead, and what lead is there is very easily leachable, potentially suggesting it's some kind of contaminant that's been added in. Strontium isotope compositions also suggest very low source rubidium-strontium ratios, which is the exact opposite of what you would expect from creep, and much more in line with what you would expect from a ferroan anorthosite source. And then finally, just the fact that the ages, as I said, for the argon, but also for these mixing ages, they're very young for what we would expect for the anorthositic crust, and it potentially aligns actually with what we see for some large basin-forming events, particularly on that older age range. You might even be up there with Anna Chernok's suggestion for the Serenitatis Basin. So I would tentatively suggest it's more likely that this is an impact-induced mobilization of lead on the lunar surface that's caused this. And then just to sort of start closing up, what about other ferroan anorthosites? Well, there is some data in the literature. We need to start getting some more new data, but certainly it looks like based on some Apollo 16 ferroan anorthosites, there probably is similar mixing. So 15415 is these top 3 points up here, but then there are several other Apollo 16 fan rocks which have similar compositions, maybe potentially looking at slightly younger mixing ages, so it could be Imbrium related. So finally, just to close up with some implications and future directions. So I think the Apollo fans suggest that you have a small but very significant creep component in terms of lead isotopes. I would suggest this most likely represents the mobilization of lead during large basin-forming impacts. However, we can't completely rule out the mixing of creep as the sources were forming. We need to look into this in a bit more detail. But there's clearly very valuable insights to be gained from looking at these crustal rocks, and especially looking at far side and non-PKT highland rocks. So I've got a talk at METSOC next month. And you can look at the abstract already for that, looking at a lunar meteorite with some interesting fan clasts. And then we're going to have some great new sample return missions. Well, we've obviously got Chang'e 6 to look forward to very soon, and then the Artemis missions coming up. So I will leave it there and say thank you very much.
Thank you very much, Josh. We've got time for one quick questions. Yeah, question at the back.
Hi, Josh. Anna Chernok, University of Trieste.
Hi,
one
Anna.
of your early plots showed potential terrestrial contamination. I was just wondering, what do you think? How does this lead get into your perfect plagioclase crystal?
In terms of the terrestrial lead, I think you're looking at the fact that a combination of things. In this case, in our data set, it's largely the fact that you've got some like 50 years worth of the sample going between different labs and being polished and repolished and cleaned. So I think you just have progressive addition of terrestrial lead in the cracks. And we see this all the time in different samples. And certainly what's really nice or reassuring is that when we've looked at completely freshly made Apollo sections, particularly some of the basalts, compared to old fin sections of the same basaltic samples, you see that terrestrial contamination just disappears very quickly in the brand new sections. So it's reassuring to see that the curation at JSC has been very good, actually. And when they make new fresh samples, they're actually quite clean.